Hello everyone, my name is Rifat Kamarudheen and my PhD thesis focuses on plasmon-driven chemistry. In this presentation, I will be focusing on how light can be used to photothermally heat nanoparticles and how this heating can be used to grow size and shape controlled metal semiconductor core-shell nanostructures. Metals, as we all know, are rich in electrons. When metal nanoparticles are illuminated with light, these electrons get polarized and start to oscillate in response to the oscillating electric field of light. Such electron oscillation is referred to as plasmon resonance. These plasmon resonances impart strong absorption and scattering properties to the nanoparticles. For example, a 70 nanometer gold nanosphere suspended in water shows strong scattering and absorption at around 550 nanometers, which makes it look green in color. The plasmon resonances can be tuned by either changing the morphology of the nanoparticle or the refractive index of the surrounding medium, or by coating a dielectric shell around the nanoparticle. For example, upon coating a 10 nanometer dielectric shell around this gold nanoparticle, the plasmon resonance redshifts by 50 nanometers. This surface sensitivity has been utilized to make plasmonic sensors. The absorption properties imparted by plasmon resonances lead to the photothermal heating of nanoparticles. Such heating is confined to the nanoparticle surface, which allows us to drive temperature-sensitive reactions selectively on the nanoparticle surface. Furthermore, the magnitude of temperature rise is proportional to the illumination intensity. Larger surface temperatures can be achieved using higher illumination intensities, which can lead to faster chemical reaction kinetics according to the Arrhenius equation. In this project, I use these localized temperature gradients to synthesize metal semiconductor core-shell nanostructures. Photothermal heating has previously been explored to synthesize hierarchical nanostructures. However, till date it has been challenging to control their size and shape with a nanoscale resolution, as can be seen in these electron microscopy images. Often in these experiments, multiple nanoparticles are simultaneously illuminated, which leads to the generation of macroscopic collective heating effects instead of nanoscale temperature gradients, and hence the synthesis of uncontrolled large structures. As such, illuminating a single nanoparticle at a time is essential to exploit nanoscale temperature gradients to grow core-shell nanostructures in a controlled manner. In order to illuminate single nanoparticles, I first dropcast a dilute suspension of gold nanospheres on a quartz substrate and build a flow cell around it. A temperature-dependent gold Syria core-shell nanoparticle synthesis is chosen to demonstrate the photothermal growth concept. We introduce the Syria reaction mixture to the flow cell and mount it onto a dark field microscope coupled to a spectrometer. This is how a typical dark field image of the substrate looks like. The green bright scatterers represent the individual gold nanospheres. In a typical experiment, I first select a single nanoparticle by closing a slit around the nanoparticle and measure its plasmon resonance. I then illuminate this nanoparticle with a focused 532 nanometer continuous wave laser to photothermally heat up the nanoparticle and grow the Syria shell around it. After 15 minutes of illumination, the plasmon resonance of the same nanoparticle is measured and a redshift of roughly 70 nanometers is observed due to the growth of a Syria shell. Electron microscopy and energy dispersive X-ray maps of the illuminated nanoparticle was performed to confirm the growth of Syria shell. Next, I wanted to explore the possibility of controlling the size of the photothermally grown Syria shell. In theory, by modulating the illumination intensity, the nanoparticle temperature can be varied, thereby allowing us to control the reaction kinetics and thus the shell thickness. In this graph, the calculated nanoparticle temperature increase is plotted on the x-axis for 35 different single particle experiments, and the corresponding redshift of the plasmon resonance after 15 minutes of illumination is plotted on the y-axis. The shell growth, which is represented by the red shift, scales with the nanoparticle surface temperature until it reaches a plateau at around 200 degrees Celsius. This temperature represents the bubble formation in the liquid, which prevents further shell growth. After exploring size control using the photothermal synthesis technique, I explored the shape control of the coastal nanostructures. In theory, photothermal effects should generate isotropic temperature profile around the nanosphere, which should produce isotropic coastal nanoparticles. To assess the morphology of the coastal nanoparticles, I measured the plasmon resonance of the nanoparticles at polarizations parallel and perpendicular to the laser polarization before and after the shell growth. Isotropic shell growth would lead to the same plasmon resonance shift at any polarization. In my experiments, I observed similar redshifts at different polarizations after the serial shell growth as seen in this graph. Furthermore, I performed such polarization-dependent measurements on multiple nanoparticles and plotted the redshift when the polarizer is kept orthogonal to the laser polarization and the redshift when the polarizer is kept parallel to the laser polarization. I observe an excellent 1:1 correlation confirming the isotropic shell growth, which is also consistent with the electron microscopy images. Till now, my measurements have been focused on understanding the morphology before and after the shell growth. To understand the growth kinetics of the Ceria shell during illumination, I also continuously collected the photoluminescence of the metal nanoparticle during the photothermal shell growth. It is well agreed that the photoluminescence spectra follows the plasmon resonance of the nanoparticle. By following the photoluminescence peak and combining it with optical simulations, I was able to extract the shell growth kinetics in real time. In this example, 90% of the shell growth is completed in roughly 10 minutes and leads to a growth of 8 nanometer Ceria shell. To demonstrate the versatility of the photothermal growth technique, I explored the synthesis of ceria, zinc oxide, and zinc sulfide semiconductors over gold nanoparticles. The left graph shows the plasmon resonance of the nanoparticle before and after illumination, and the right graph shows the polarization-dependent spectra after the shell growth, indicating isotropic shell growth. Similarly, I grew zinc oxide over single gold nanospheres where the plasmon resonance exhibited multiple peaks after illumination. The multiple peaks are a signature of thicker zinc oxide shells. The grown shells were isotropic as can be seen in the right graph. Similarly, I was also successful in synthesizing isotropic zinc sulfide shells on single gold nanospheres using the photothermal synthesis technique as can be seen in these graphs. Furthermore, I used this photothermal technique to demonstrate the concept of substrate patterning and growing different semiconductors on the same substrate. This image represents gold nanospheres deposited on a quartz substrate. They scatter in the green region since they have a plasmon resonance around 550 nanometers. I first introduced a ceria growth solution and photothermally heated this nanoparticle, which turns into red due to the growth of a ceria shell and the subsequent redshift of the plasmon resonance. I then flushed the flow cell with water and introduced a zinc oxide precursor and illuminated the second nanoparticle, which turns into yellowish orange in color because of zinc oxide shell growth. I flushed the flow cell again with water and introduced the zinc sulfide precursor and illuminate this third nanoparticle, which turns red due to zinc sulfide shell growth. In conclusion, the photothermal growth technique can be used to grow size and shape controlled hierarchical nanostructures. The shell growth kinetics can also be monitored in real time, giving additional control over the synthesis. This versatile technique can be used to pattern two-dimensional substrates. Thank you.